Welcome to the deep dive. We've all heard the headlines about AI models achieving incredible accuracy in the lab. But have you ever stopped to think about what happens when, say, that super accurate model for detecting depression from social media posts completely misses sarcasm, or maybe misinterprets cultural nuances? That could lead to false alarms, or worse, missing critical warning signs. Or what about that financial fraud detection model? It might have a high correctness score, technically speaking, but ends up disproportionately flagging transactions from specific demographic groups. That causes real harm, real frustration. These aren't just hypotheticals. They really hit home that a high accuracy score on some test set is not a guarantee of real-world success, or reliability, or fairness. A technically accurate model can actually be practically useless, or even actively harmful. And that's exactly what we're exploring today. Our mission in this deep dive is basically to give you a shortcut to understanding a brand new and absolutely critical engineering discipline, AI model testing. We're going to uncover why it's fundamentally different from traditional software testing, what core components of an AI system need really rigorous scrutiny, the essential skills for this emerging field, and also a practical multi-phase framework, plus the industry standard tools used to build truly trustworthy AI. By the end, you'll gain knowledge quickly but thoroughly, discover some surprising facts, and hopefully get those aha moments about the true complexities of AI quality. So, we constantly hear about AI achieving amazing accuracy, but as those opening examples showed, that's really just the tip of the iceberg. Why is simply being accurate not enough for an AI model to be considered, successful in the real world?
Yeah, it's a great question. And what's fascinating here is the fundamental shift in mindset required. You see, in traditional software testing, we're all about verification,
Verification, okay.
right? Ensuring code executes according to predefined, explicit rules. You expect a precise, predictable output. It's kind of like checking if every single step in a recipe is followed exactly.
Makes sense.
But with AI, it's about validation. AI systems are probabilistic. Their logic is learned from data, which, well, can lead to emergent and often unpredictable behavior.
So less predictable.
Exactly. So we're not just checking if the code runs, we're testing to confirm a model will perform correctly, reliably, and responsibly in its intended operational environment. We have to focus on its statistical properties, its fairness metrics, acceptable ranges of behavior. It's quite different from looking for exact, deterministic outputs. And this really requires a new engineering discipline, one focused on continuously interrogating the model's behavior, building resilient systems, ensuring fairness, and crucially, mitigating harm throughout the entire machine learning lifecycle.
That's a huge conceptual shift. It sounds like we're inherently accepting a degree of unpredictability with AI then.
In a way, yes. Or rather, managing that unpredictability.
And if so, how do you even define the acceptable ranges of behavior for something that's probabilistic? That sounds tricky.
It is tricky. It involves defining thresholds, acceptable error rates for specific contexts, and often looking at performance across different segments of users.
Okay. And it sounds like it's not just about testing the AI model itself in isolation. I understand there are actually three critical components or pillars in an AI application that demand rigorous testing. Can you walk us through those?
The first one, and arguably the most important, is data.
Right.
It's truly the foundation of all AI.
Absolutely fundamental.
We all know the garbage in, garbage out principle, and it's absolutely true here. Flaws like biases, inaccuracies, or maybe poor representation in training data, they will be learned and amplified by the model.
They get baked right in. Exactly. So this means testing your data is the first and most critical phase. It's about preventing failures before training even begins. Then number two, we have the model itself. This is the core learning component.
The brain, as you said earlier.
Right, the brain. Here, testing involves interrogating its learned behaviors, evaluating performance on data it's never seen before, assessing its robustness against, say, adversarial inputs, probing for fairness, and ensuring explainability where it's needed. This is where the AI truly lives. And finally, there's the code. This is the more traditional software component that wraps around the model.
The plumbing, almost.
Yeah, like the data pipelines, the APIs that serve predictions, the user interfaces. This surrounding code still needs traditional software testing methods. Check for correct functionality, proper integration with the model, graceful error handling. All three have to be rock solid.
Which leads to an important question. If AI models are probabilistic, and often these black boxes, how do we even begin to test them effectively when we can't always see inside their internal logic?
Good point.
Well, first, let's talk about non-determinism. AI models can actually produce slightly different outputs, even with the same inputs.
Really? Why is that?
It's often due to stochastic elements like random weight initialization during training or random sampling in certain algorithms. So this means testing has to focus on aggregate performance and behavioral consistency across many data points,
Yeah.
rather than relying on single input-output checks like you would in traditional software.
Okay, so looking at the big picture performance.
Precisely. Second, there's the black box nature you mentioned. For many complex models, especially deep neural networks, their internal decision-making processes are pretty opaque. And here's where it gets really interesting. This opacity transforms AI testing into something like, well, a form of scientific inquiry.
Scientific inquiry, how so?
Think about it. In traditional software, if something breaks, you trace the code line by line, right? You find the bug. But with AI's black box nature, it's more like we're archaeologists trying to deduce the behavior of an ancient civilization from its artifacts. We can't read its blueprints directly. So testers have to design experiments to probe the model's behavior externally, form hypotheses about its internal state, and use techniques like explainability testing, LIME, and SHAP are common examples, to try and get some insight into why a model made a specific prediction. They show the most influential inputs.
So you're testing its behavior and trying to infer the why.
Exactly. And third, unlike traditional software, which is static until you release a new version, AI models are dynamic and evolving.
The drift issue.
Right. You might build a perfectly accurate model today, but here's the surprising truth. AI models aren't set and forget. The world changes, and if your model doesn't keep up, it could become irrelevant or even dangerously wrong almost overnight. Their performance can degrade over time in a process we call drift, either data drift, where the input data changes, or concept drift, where the relationship between inputs and outputs changes. Think about a model trained on pre-pandemic economic data. It might fail spectacularly post-pandemic. This dynamic nature absolutely necessitates continuous monitoring once a model is deployed.
So, wow, we're not just dealing with complex code, we're dealing with this living, breathing, sometimes unpredictable entity that learns and, as you said, can even sort of forget or become outdated. That really elevates the challenge of ensuring quality.
It really does.
This sounds like a completely different breed of engineer is needed for this work. What kind of expertise, what kind of person does it take to excel as an AI test engineer?
Well, for starters, you definitely need solid technical proficiency, strong programming skills, especially in Python, familiarity with data science libraries like NumPy and Pandas, ML frameworks like scikit-learn, TensorFlow, PyTorch.
The usual suspects. Exactly, and test automation frameworks like PyTest. Plus, you need an understanding of MLOps tools and practices, things like cloud platforms, CI/CD pipelines. That's continuous integration and continuous delivery, basically automating your testing and deployment. Docker, too. Then there's ML literacy. You need to understand core ML concepts, supervised, unsupervised, reinforcement learning, and crucially, how testing changes for each type.
Right, testing a recommendation engine is very different from testing an image classifier.
For sure. You need to grasp model internals, like how deep learning scales with data, and also emerging areas like generative AI and prompt engineering. That includes knowing how to evaluate for things like hallucinations, misinformation, and bias in those newer models. Next up is analytical and critical thinking. This means having a working knowledge of statistics and probability for model evaluation. An intuitive grasp of linear algebra and calculus helps too, maybe understanding gradient descent, for example.
It's not just about running tests, it's understanding the math behind them.
Precisely. And strong systematic problem-solving skills are key to debugging those complex, non-deterministic AI failures we talked about earlier. And finally, maybe one of the most important, collaboration and communication. You need the ability to work effectively with cross-functional teams, data scientists, ML engineers, product owners.
Breaking down those silos.
Absolutely. And you have to be able to clearly and concisely communicate test findings, especially about tricky issues like bias or unexpected behaviors, to stakeholders who might not be technical experts.
Yeah, that communication piece is huge.
Yeah.
If we connect this to the bigger picture, this role isn't just about finding bugs in code. It's really about being a crucial guardian of quality, trust, and responsibility.
A guardian, I like that.
And there's actually a very practical three-phase framework that maps this whole comprehensive testing journey directly onto the machine learning lifecycle itself.
Okay, let's break that down. What's phase one?
Phase one is pre-training, essentially data validation. This is often the most critical and, kind of surprisingly, sometimes the most neglected phase. Why? Because of that garbage in, garbage out principle we keep mentioning.
Right, fix the problems early.
Yeah, exactly. It's proactive. It prevents failures before you even invest time and resources in training a model. Key techniques here include data quality and integrity checks, things like checking for missing values, making sure data types are correct, values are within expected ranges. You'll also do schema and distribution validation, checking the overall structure, the statistical properties of your data. This acts as a first line of defense against data drift later on. And crucially, you perform bias and fairness assessment of the data itself. Identifying issues like imbalanced classes or underrepresentation of certain demographic groups early allows for mitigation strategies before the bias gets baked into the model.
Okay, so really scrutinizing the raw material. Are there specific tools for this?
Yeah, a great tool here is called Great Expectations. It allows you to create these declarative unit tests for your data in something called an expectation suite. The cool thing is, it's human readable, it's version controllable, and it can produce these reports called data docs for clear, shareable summaries. For example, you could set expectations like customer IDs must be unique, gender values must be one of these specific options, or monthly charges must be within this range.
Unit tests for data, that's a neat concept. What's phase two?
Moving on to phase two, offline evaluation or model in lab. Now, this phase goes far beyond just calculating a single accuracy score for your trained model in a controlled lab-like environment. A best practice here is using what we can call an AI tester's balanced scorecard. Gives you a much more holistic view.
A scorecard, okay. What's on it?
Well, it covers several dimensions. First, correctness, using metrics beyond basic accuracy, like F1 score, which is great for imbalanced tasks like rare disease prediction, or R-squared for regression tasks like predicting house prices, or maybe NDCG for checking the quality of rankings, like in search engines. Then you have robustness. This could be measured by something like adversarial success rate. How easy is it for tiny, almost invisible changes to an input to make the model fail? Think about a self-driving car's vision system being tricked.
Scary stuff.
Definitely. Then fairness, using metrics like disparate impact. This compares favorable outcomes for protected groups versus privileged groups. A common threshold is if the ratio is below zero point 0.8, it often indicates bias, say, in loan approvals. We also look at explainability, assessing things like feature attribution stability. Does the model consistently rely on relevant features for its predictions, especially in critical areas like medical diagnosis? And finally, performance in the traditional sense, things like inference latency. How long does it take for the model to make a single prediction? Crucial for real-time bidding systems, for example.
Wow, that scorecard sounds incredibly robust and thorough. But practically speaking, does adding all these rigorous testing phases significantly slow down the development and deployment of AI models, especially maybe for smaller teams or startups?
That's a really great question, and it's a valid concern. It can add time initially if you're doing it all manually, but that's precisely why automation becomes so absolutely critical, which we'll definitely get to when we talk about MLOs.
Okay, automation is key.
Yes. But sticking with this offline phase for a moment, alongside the scorecard, we also use powerful behavioral testing techniques. These include robustness testing, like stress testing with extreme inputs, edge case testing for rare scenarios you might not have much data on, and that adversarial testing we mentioned, crafting inputs specifically designed to cause failure. Super important for high-stakes applications. Then there's specific fairness and bias testing. This involves running the model on data sliced by sensitive attributes, race, gender, age, whatever is relevant, and comparing performance metrics across these different groups using fairness metrics like predictive parity or equalized odds.
So actively looking for disparities.
Actively looking. And finally, explainability and interpretability testing. This isn't just about generating explanations from tools like LIME and SKAB, but actively validating if those explanations are stable and actually make sense, if they're plausible. And for this behavioral testing, particularly for NLP models, language models, a powerful tool is Checklist. It lets testers move beyond just aggregate metrics like accuracy and test-specific linguistic capabilities.
Like what?
Things like understanding vocabulary, handling negation properly, recognizing synonyms, things like that. It provides much more actionable insights. Instead of just saying accuracy is 85%, it might tell you this model fails 60% of negation tests. Much more useful for improvement.
That is much more specific. Okay, so we've validated the data. We've done intensive offline testing. What's phase 3?
Finally, we get to phase 3, online evaluation or model in production. Because while all that offline evaluation gives you confidence, the ultimate final arbiter of a model's quality is how it actually performs on live real-world traffic.
Where the rubber meets the road.
Yes, exactly. Key techniques here include A/B testing. This is really the gold standard for measuring the actual causal impact of deploying a new model versus maybe the old one, or no model at all. You randomly split your users or traffic, show one group the new model, one group the old, and compare key business metrics, things like user engagement, conversion rates, revenue. Companies like Spotify use this extensively for testing complex recommendation algorithms.
So direct comparison in the real world.
Right. Another important technique is canary deployments. This is more of a risk mitigation strategy for rolling out a new model safely.
Canary like the coal mine.
Precisely. You release the new model to just a small subset of users, first, say, 1% or 5%. You monitor its technical performance very closely, error rates, latency, etc. If any issues pop up, you can immediately roll it back with minimal impact. Big companies like Netflix and Google use this extensively.
Makes sense for managing risk.
And absolutely essential in production is continuous monitoring for drift and degradation. You need automated systems that are constantly comparing the statistical distributions of the live input data and the model's predictions against a baseline, usually from the training data or a trusted earlier period. This helps detect that data drift or concept drift we discussed. If significant drift is detected, it can trigger alerts for investigation or even kick off an automated retraining pipeline.
And are there tools for this continuous monitoring part?
Yes, definitely. A popular open source option is Evidently AI. It's a Python library specifically designed for evaluating, testing, and monitoring ML models in production. It really excels at detecting drift and degradation by generating these interactive visual reports. For example, you can generate a data drift preset report or a classification preset report that clearly shows differences between your reference data and your current production data.
Okay, interactive reports sound useful for spotting problems quickly.
They are. It helps visualize where things might be going wrong.
This is, well, it's a lot of rigorous testing. It's becoming really clear why manual methods just wouldn't scale or be reliable enough. So how does all of this fit together in a real-world production environment? How do you make it an automated, seamless process? Because this is where it gets really interesting, right?
Yeah.
This is the domain of MLOps, or machine learning operations.
Exactly.
MLOps. It's essentially taking the principles we know from DevOps, things like continuous integration, continuous delivery, automation, and applying them specifically to the unique components of an AI system, the data and the models themselves.
Couldn't have said it better myself.
And this all forms what's known as a continuous training, or CT pipeline. Think of it maybe as an automated workflow. A developer commits some code, maybe a change to the model architecture or the feature engineering. That commit immediately triggers the pipeline. First, automated data validation kicks in, maybe using great expectations like you mentioned, acting as a quality gate. Does the new data meet our standards?
Crucial first step.
If the data passes, then automated model training occurs. The system trains a new version of the model. That new model then automatically undergoes automated model validation, running those offline tests, maybe using checklists or custom scripts, checking that scorecard.
The automated checks.
If it passes those tests, it gets versioned and registered in a model registry, a central place to keep track of models. Then automated deployment to production can follow, using those safe strategies we talked about, like canary deployments.
Controlled rollout.
And finally, once it's live, continuous monitoring, perhaps using Evidently AI, constantly watches its performance, checking for degradation and drift, and sending automated alerts if anything looks off.
That automated workflow is the essence of MLOps. It transforms testing from this potentially manual, error-prone, maybe inconsistent task into a consistent, repeatable, and enforceable process. It builds quality in. But, beyond just the automation itself, there are two principles that are really paramount for building truly trustworthy AI systems within this MLOps framework: comprehensive versioning and robust governance.
Okay, tell me more about versioning everything. Why is that so important?
Well, versioning everything is critical because reproducibility is absolutely paramount in machine learning. If a model starts behaving strangely in production, or if you need to audit a decision it made months ago, you must be able to recreate the exact conditions under which it was built.
To trace its lineage.
Precisely. And that means versioning not just the code, but also the data used for training the exact snapshot and the resulting model artifacts themselves. Everything that went into creating that specific model version. Tools like DVC, which stands for Data Version Control, and NLflow are vital here. They help track experiments, the parameters used, the resulting metrics, and the models themselves, allowing for full traceability and the ability to easily roll back if needed.
MLflow sounds useful there.
Oh, MLflow tracking specifically is fantastic. Think of it as the central lab notebook, or maybe the system of record, for your entire machine learning experimentation process. For every single training run, it tracks the hyperparameters you used, the metrics it achieved, like accuracy, F1 score, AUC, whatever you care about, and even artifacts like plots, say confusion matrices for a churn prediction model.
Hmm.
It makes development transparent, comparable, and crucially, reproducible. And that reproducibility is a prerequisite for systematic, reliable testing.
Got it. Track everything, version everything. What about governance?
Right, governance and compliance. As AI becomes more deeply integrated into high-stakes domains, finance, healthcare, autonomous systems, formal governance becomes, well, non-negotiable. You simply have to have it. Frameworks are emerging to help with this. Things like the NIST AI Risk Management Framework or the international standard ISO IEC 42001. They provide structured guidance for actually managing AI risks throughout the lifecycle. And these frameworks directly drive testing requirements, particularly for ensuring fairness, accountability, transparency, and safety, often summarized as the FAIR principles, though that acronym gets used in different ways. This structure ensures that testing isn't just a technical task, but a core part of responsible AI development and deployment.
That's fascinating how these formal frameworks are starting to shape the engineering practices. And actually, for you, our listener, if you're looking to gain practical experience or maybe showcase these kinds of skills, we came across a really cool portfolio capstone project idea that pulls pretty much all this together end to end.
Oh,
It's a customer churn prediction project. But the key goal isn't just getting the highest possible accuracy score. The real goal is demonstrating a professional, rigorous process of validation and quality assurance right from data ingestion all the way to simulating deployment. It integrates all the concepts we've been talking about. A well-organized project structure, automated data validation, perhaps using great expectations, systematic model training, and experiment tracking with ML flow.
Covered all the bases.
Exactly. Fairness and bias testing, maybe using a library like FairLearn, and even simulating deployment and monitoring with something like a simple Flask API, and using evidently AI to check for drift on simulated incoming data. And the sources emphasize the crucial importance of a comprehensive reanimate MD file for a project like this. It's about telling the story to a potential employer. Look, I don't just build models, I build reliable, fair, and robust AI systems.
That's a fantastic point. The narrative around the projects is almost as important as the code itself for demonstrating that broader understanding of quality.
So wrapping this all up, what does this journey mean? We've gone from understanding why just looking at basic accuracy falls way short, all the way through to a comprehensive framework for building truly trustworthy AI systems. We've seen how this new engineering discipline is emerging right at the intersection of data science, software engineering, and increasingly ethics.
Indeed. And the role of an AI test engineer, as we've discussed, it really transcends mere technical expertise. It genuinely becomes a position of profound responsibility. You're acting as a guardian of safety, a champion for fairness, and an architect of trust between humanity and these intelligent creations we're building. The skills we've outlined here today, they aren't just a pathway to a rewarding career, although they certainly can be. They are really the tools necessary to help build an AI-powered future that is not only effective and powerful, but also equitable and safe for everyone.
A powerful thought to end on, which leads us to our final provocative thought for you, the listener. Considering the increasing autonomy and the really deep integration of AI into these high-stakes domains, we're talking self-driving cars, medical diagnosis, managing financial markets, what ethical questions might arise when a model's learned behavior, even after rigorous testing, leads to unforeseen negative consequences? Consequences that even the best testing didn't anticipate. And looking ahead, how might the discipline of AI testing itself need to further evolve to proactively address these increasingly complex, perhaps even philosophical challenges?